Hello everyone and welcome to our webinar today. The presentation is titled The Downstream Effect of Lubricant Contamination and the Value in Controlling It. My name is Ashley Stromek and I am a Customer Engagement Specialist here at Test Oil. Just wanted to let everyone know that you are on mute, and if you have any questions, please feel free to type those in the GoToWebinar application. Everyone is on mute today so we can ensure a high quality recording. That recording will be distributed after the presentation is over, along with a brief survey. Test Oil is happy to present this webinar in conjunction with DeskCase and glad to have Jason Kopczynski as our presenter. Jason is the Director of Reliability Services for DeskCase. He has extensive experience coaching clients in asset reliability and lubrication management. Jason has also published a variety of technical articles on condition monitoring, contamination control, lubrication management, and program management, and has been invited to speak at numerous international symposia. Jason, if you're ready, you want to take over?
I am all set. Thank you very much. Thanks for joining me today, everyone. I'm really excited to present the material today. I titled this A Downstream Effect of Lube Contamination and the Value in Controlling It, because I think there's some fundamental ideas that we all understand and we can all accept, but I think sometimes we don't know the true value or the true financial impact of some of the decisions that we're making, or rather the decisions we're not making. So today I'm going to talk about lube contamination, how it affects our machines, how it affects our lubricant, and really what the financial impact is downstream. What we have to understand is there are several things that we do or may not do today that doesn't necessarily affect our lubricant or our machine tomorrow or next week or next month, but rather if the machine is designed to last 15 years and we're seeing a relative useful life of perhaps only 5 or 6 years, there is an impact financially speaking that we have to address. We're losing out a lot of production years of our equipment simply because some of the things we're not really doing well or not doing at all. So that's really the basis of the conversation this afternoon, and I could really talk for many hours on this, but we have an hour to cover what I consider a very important topic. So what I'd like to do first is I'd like to kind of talk through a survey, a reader survey we did back in 2011, and we reached out to the readers of Machinery Lubrication magazine and we asked them, how important is precision lubrication to overall equipment reliability? Now, I'm sure you can understand this is a lubrication trade magazine. It's dedicated to lubrication best practices. Everyone who receives the magazine subscribes to the magazine, so we kind of understood the readership of this technical magazine has a specific interest in lubrication. So when we asked the question how important lubrication was to overall equipment reliability, we weren't really surprised by the results that we got back. 81% said that lubrication was critically important to overall equipment reliability. 18% felt it was important but not critical, and less than 1% felt otherwise. So really what we're talking about is just over 99% of all respondents felt precision lubrication was important or critically important to overall equipment reliability. So again, no real surprises there. So we asked a follow-up question. We felt that, well, if everyone feels it's important or critically important, then everyone must be doing something about it. So we asked, at your plant, have you achieved a level of lubrication you'd consider close to best practice? And this is where, the results became a little bit surprising. What we got back was that about a third of respondents felt that they had achieved a level of lubrication that they would consider close to best practice, and 2/3 had not. 99% of all respondents felt it was critically important or important, but only a third of them were doing anything about it. And I really feel like if we were to address those third of plants who felt they were doing anything close to best practice, we'd still find lots of room for improvement. And one of the reasons for that is we tend to, in the plant environment, we tend to benchmark ourselves against a previous version of ourselves. You know, if we've worked in a plant for 10 or 15 or 20 years, we know that, well, 5 years ago we were really bad, you should have seen us then, and now we're so much better. And yes, you may have made some significant improvements and you're better than you were a few years ago, but relative to what industry best practice would suggest you should be at, there's still a lot of room to grow. So we took a look at these results and we really tried to understand what were the roadblocks, you know, what was happening in these plants keeping them from moving towards best practice in lubrication. And we kind of boiled it down to 3 main roadblocks, right? The first one is the one that we're going to address today, and this is really the lack of knowledge or understanding of what's possible. Most people don't understand the impact of poor lubrication and contamination downstream. You know, they feel like, well, if there's water in my oil, yeah, that's a significant problem, let's get it out. It's more of a nuisance than it is a root cause. So we're going to talk about the lack of knowledge and understanding of what's possible. We do know that there's other roadblocks, including, you know, just being simply too busy. We've all got, you know, 50 or 60 hours worth of work to do in a 40-hour work week. You know, we've got to, you know, we're doing more with less resources today than ever before. And then, of course, we'll also sort of address this afternoon as well, where we're talking about the lack of management buy-in to provide the funding. As maintenance personnel, reliability personnel, engineers, we talk in very technical terms. When we're trying to illustrate the challenges we have in lubrication and specifically contamination control, there's an investment that needs to be made to overcome some of these challenges. And our job is to convey what we know about lubrication, contamination control, and reliability, and convert that to a language that management can understand. And unfortunately, as technical folks, engineers, and reliability folks, we're just not really good at that. So we'll talk a little bit about that this afternoon. But I think that's where we're going to kind of frame out the rest of the conversation, talking about the lack of knowledge or understanding of what's happening and what's possible, and then how to really convert what we know about reliability, lubrication, and contamination control into a language our management team can understand, and not just understand, but get behind it and really support it. So let's talk a little bit about the role of lubrication and machine reliability, because I think this is really where, you know, the fundamental aspect of contamination control comes from. There was a study that ExxonMobil did many, many years ago at a paper mill in the United Kingdom. And one of their conclusions was that less than 0.5% of a plant's maintenance budget was spent on purchasing lubricants. And we could all probably agree with that. We don't, of our maintenance budgets today, we don't spend a huge percentage of our maintenance budget, you know, just buying lubricants. But they concluded that the downstream effect of poor lubrication can impact as much as 30% of a plant's total maintenance cost each year. So putting that in perspective, ExxonMobil feels that a plant has, say, a $10 million maintenance budget. They're losing $3 million of that every year to the downstream impact of poor lubrication. You know, so it's important that we look at what poor lubrication is. And it means many things to many people, but we need to kind of define that in a holistic way. It's not necessarily just the quality of the lubricant itself. It can be the quality of the lubricant, but it's many other things. It's too much lubricant, too little lubricant, the wrong lubricant, maybe the right lubricant with the wrong additives. Could be the poor contamination control or non-existing contamination control. Could be poor storage and handling, poor dispensing. When we talk about lubrication, we're talking about the act of, you know, performing the job in our plants. So it can be all of those things, and usually it's all of those things combined which are causing the most problems. So we have to understand, you know, before we get into, you know, the downstream effect of contamination, we have to understand what causes machines to fail. And we all know that machines, as they rotate or reciprocate, that they wear. And the job of a lubricant is to separate those mating surfaces to eliminate or reduce the amount or potential amount of wear. Now, Professor Ernest Rabinowitz spent a lot of time in his career at MIT doing research on what he called the loss of usefulness. Within his research, he found that about 70% of why machines fail was due to surface degradation. So a kind of a fancy way of saying machines are wearing out. And of that 70% of machines that are failing due to wear, 20% was due to corrosive wear. So acids, moisture in the oil, corroding the internal surfaces of our components. But most of it was due to mechanical wear. So when we look at the causes of machines wearing and how this mechanical wear actually occurs, we can kind of reduce it down to 2 or 3 or 4 main culprits here. Where we're talking about things like abrasion, erosion, and fatigue. When we're talking about abrasion, erosion, and fatigue, we're talking about wear modes that are directly due to particle contamination. And if we look at this closely, we know that 82% of mechanical wear is caused by particle contamination. Not because of water, not because of acids or deposits, but because of particle contamination. So it would stand to reason that if 82% of mechanical wear is caused by particle contamination, then we should really focus on the number one contaminant being particles. Okay, so let's talk about abrasion, erosion, and fatigue for a little bit. Three-body abrasion requires a third body, and that third body is a particle. And what you'll notice that's interesting about the particles in the image on your screen here is that those particles are almost exactly the same size as the opening that they're embedding themselves into. If these particles were much larger than that opening or that clearance, the particles wouldn't fit inside. They wouldn't jam themselves in and get embedded into the soft surface. And if they were much smaller than the clearance, than the opening of these two mating surfaces, they would simply float on through, right? So it's important that we understand that that those clearance sizes are different for every component, and we should be focusing on the most critical components of our system when we're looking at filtration and what types of, what size of particles to filter. But we're really looking at the clearance size particles, and we generally say that the clearance size particles are somewhere in the neighborhood of 2 to 5 microns in size. So if we're targeting 10 micron particles or 15 or 20 micron particles, we're not targeting the clearance size particles, the ones that are causing the most damage. So with three-body abrasion, we've got two types of three-body abrasion. We've got plastic flow or plastic deformation, and we also have cutting where that occurs because of three-body abrasion. So in plastic flow or plastic deformation, we have a clearance size particle that embeds itself into one of the mating surfaces, typically the softer surface of the two, and then it basically plows against the opposing surface, creating a berm which has several subsurface fatigue cracks in it. That berm will eventually break off, potentially going downstream, causing more problems. With cutting wear, is due to the shape of the third body particle. Again, it embeds itself into the soft surface, but it typically has a very sharp edge on it, and that sharp edge then goes and scrapes along the opposing surface, pulling off a very distinct shape of wear debris. Looks like a corkscrew. It's serrated on the edges. It's very sharp, and it's typically quite large. But they go on to cause a lot of damage within our systems. And really the only way to stop this is to eliminate or remove the clearance size particles or by increasing the oil film's thickness beyond the size of those particles. Erosion wear, this is something that typically occurs in high-velocity hydraulic systems. This is essentially what I like to call sandblasting on the inside of a hydraulic system, where we've got a lot of solid particles traveling at a high velocity through a hydraulic system, and when they meet the surface of the inside of the machine or change directions, they're basically rubbing themselves up against the surface, pulling material off as they strike the surface. Again, the way to stop this is to eliminate the particle contamination. And then, of course, contact fatigue. This is something that we see quite often, especially in rolling element bearings. But again, this is a clearance-sized particle that exists between the surfaces and the rolling contact bearings, and it generates a high amount of pressure. It's very localized. And again, it causes these berms and these subsurface fatigue cracks. Eventually, those fatigue cracks will make their way to the surface and will have a significant amount of pitting or spalling in the rolling elements. So again, the only way to really eliminate this is to increase the oil film thickness or to eliminate the particle contamination. So let's talk a little bit about contamination now. So we're talking about solid particle contamination because we know that 82% of mechanical wear is caused by particle contamination, and this is a pretty significant finding. So if we want to reduce the amount of wear in our systems, we should probably be focused on particle contamination. But really, when we're talking about contamination, we can be talking about several things, and it's important to understand that as well. So when we talk about contamination, when we actually define what contamination is, it essentially is anything that doesn't belong in the oil, right? So we're talking about, of course, dirt and solid particles, but we're also talking about things like water. Sometimes it's a big nuisance. Other times it's actually very detrimental and dangerous to the lubricant. Air, again, is something that could potentially just be a nuisance, but in fact it does have direct machine wear effects. It can damage the lubricant and has indirect damage downstream. We're also talking about things like wear debris. Wear debris acts as a catalyst for oxidation, which damages the lubricant and then goes on to damage our machine surface. We also have to look at things like other lubricants. Even if we have very, very clean lubricant, we've pre-filtered our new oil and we've taken all the solid particles out. If it's the wrong lubricant, it's going to be just as dangerous and as detrimental to the piece of equipment. In mobile equipment, fuel contamination, coolant contamination, if we've done system flushing or some type of cleaning or repair or rebuild or an overhaul, detergents and other chemicals can also be damaging to the lubricant and to the piece of equipment as well. So some of the common effects of contamination, we'll focus on particle contamination for this conversation because, again, I think this is the location where we're going to have the biggest bang for our buck. If we focus on controlling particle contamination, we're going to see pretty significant results right away. So particle contamination, direct machine wear, we've talked about abrasion, erosion, and fatigue. In valves, we'll have something we call valve stiction or silt lock, where we have many very tiny silt particles kind of building upon one another, causing spools and valves to lock up and not be responsive. So those are the direct machine wear mechanisms that we need to be careful of. But we also see damage to the lubricant as well. When we have particles in the lubricant, particles oftentimes act as a catalyst to oxidation. Now, oxidation is really just the natural degradation of the lubricant. It's not something that we can stop or reverse. We can really just slow it down using lubricants with antioxidants. But as the lubricant ages and catalysts are allowed to reside within the lubricant, things like water, solid particles, air, these are all catalysts to oxidation. The oxidation then goes and creates these acidic byproducts, deposits, varnish, this type of thing. And that has certainly damaged the lubricant and indirect damage to the machine downstream. We might also see particle scrubbing where additives are removed because of the particles in the lubricant. And oxidation also causes the viscosity to increase as the chemical makeup of the lubricant changes over time as the lubricant oxidizes. And then the indirect damage, as we mentioned, varnish deposits. As oxidation occurs, it creates these acidic byproducts which are corrosive. We might also see some increased aeration. Aeration just further exacerbates the problem because air is also a catalyst for oxidation. So particle contamination, not simply just direct machine wear, but damage to the lubricant and indirect damage to the machine and the lubricant in the long term as well. So a lot of things that we need to look out for when we're talking about particle contamination. Now I mentioned earlier about the particle size that we were most concerned with being the clearance size of our machines. Now we really want to focus on perhaps the most sensitive piece of equipment or the most sensitive component within our equipment, and those clearances are typically in the neighborhood of 2 to 5 microns. Some systems will have tighter tolerances, smaller clearances, maybe down to a micron. Others will have much larger clearances, but for say 90 to 95% of all our equipment, we're going to be looking at a 2 to 5 micron range being the most critical clearance sizes that we want to control. So let's talk about how big a micron is. This is very important because in the many years that I've been doing this work, I talk to a lot of people who feel like the particles that they're most interested in are the ones they could see. Simply by taking an oil sample and holding that sample bottle up to the light, a lot of people feel like they're going to be able to take a look and see particles floating by, and these are the ones that they're most interested in. And unfortunately, the particles we're most interested in are much too small to see with the naked eye. To give yourself some perspective here, the diameter of human hair is about 50 to 70 microns. It's 60 microns on average. The particles we're most concerned with are the size of blood cells, in the 2 to 5 micron range. Now the human eye, the extent of human vision can see a black dot on a white piece of paper. That's as good as it's going to get for human vision. So without instrumentation, we're never going to see these particles floating through an oil sample. We're never going to be able to feel these, rub a drop of oil between our fingers and feel a 2 or 5 micron particle. We have to trust that they're there. We can see them with instruments. Our lab is skilled at identifying these particles and seeing them and doing particle counting. And we have to trust that they're there. Just because we have a clear oil sample that we don't see any particles doesn't mean they're there. But these small particles, these microscopic particles that we can't see with the naked eye, are the ones that are causing the most damage. So we have to look at this and say, well, how much does it really take to contaminate, say, a 55-gallon drum of oil? What are we really talking about here? Are we talking about a shovel full of dirt? Are we talking about a bag full of dirt? In fact, we're talking about a lot less dirt than that. When we're talking about how much it takes to contaminate a 55-gallon drum, we're talking about 1 teaspoon of dirt in a 55-gallon drum is going to give us a particle count of 19, 17, 14. Now, if you're really familiar with the particle count, the ISO 4406-99 particle count, what you need to know is that the higher these numbers are, the more contamination exists in the sample. So a particle count of 19, 17, 14, well, that may be clean enough for a large gearbox. It's much too dirty for a very sensitive hydraulic system with servo or proportional valves. But what that really means is that there's about 1 billion particles in the drum which are 4 microns in diameter and larger, and 4 microns being right in the middle of our 2 to 5 micron clearance range for particles causing the most damage. So think about this. 1 teaspoon of dirt in a 55-gallon drum contaminates that entire drum of oil, right? Now think about your individual plants. Think about how often you're opening and closing these drums of oil. Think about how often you find a drum of new oil that's been left open, exposed to the environment of your manufacturing facility, right? Think of how many teaspoons of dirt are actually in that new drum of oil. And then we simply go and take that new drum of oil, treat it as if it were ready to use, and we include it, we dispense it into our components, and we're not sure why we've got so many problems with wear and contamination. So it doesn't take a whole lot to contaminate, right? And the next slide really is talking about the cost of particle ingression. So what if I have a lot of dirt in my new oil? What does it really matter at the end of the day? So we pulled this slide together for you because we want to kind of illustrate the cost of particle ingression. So these two systems are identical in every way. They're just for illustration, but one system operates much cleaner than the other system. They both have 65 gallon per minute pumps. They both have the same volume of hydraulic fluid. The difference really is the cleanliness of the lubricant, right? So the system on the left is operating at a ISO 232118, right? So much too dirty for your standard hydraulic system. The system on the right is operating at an ISO 171411, which is much closer to an ideal cleanliness for a hydraulic system. So if this system is running, if these systems, are running 65 gallons per minute and they're operating 24 hours a day, every day of the year, if we were to quantify the amount of dirt, like count every particle going through these pumps in a year's time at the different ISO particle counts, you're going to be really surprised at the amount of dirt that actually is, right? So the system on the left operating at an ISO 232118, if we were to quantify the amount of dirt going through that pump at that ISO code, we would count 8,800 pounds of dirt going through this pump in a year's time. On the other side of this, operating at an ISO 171411, we'd only count 55 pounds of dirt going through this pump in a year's time. Right, so you can imagine the challenge that you'd have, running almost 9,000 pounds of dirt through a hydraulic pump in a year's time. Right? We can't expect this system to last very long. In fact, the life expectancy of the pump on the left is only 2 years. Right? Not surprisingly there that it's only 2 years. The system on the right, however, the life expectancy operating in an ISO 171411 is 14 years. Right? So we have to look at this and say, well, what is the cost of changing this system every 2 years? Now, the cost is going to be different for every system. Maybe this costs $10,000, $20,000, $50,000. But operating at a very, very dirty ISO particle count, we're going to be changing this system every 2 years, right? Every 2 years, we've got to incur downtime, perhaps overtime, perhaps rush shipping, loss of production, and so on, versus the system on the right, where this lasts somewhere in the neighborhood of 14 years, right? So it's quite intuitive. When we look at this, we say, well, of course, the cleaner the system, the longer the components are going to last. And there's been several studies over the years, and we've compiled a lot of that data in this slide here, where we're talking about, relative life versus the cleanliness code. So intuitively speaking, the cleaner the system is, the more relative component life we're going to get out of that system. So if we look at the systems in the previous slide, the system on the left was operating at, say a much dirty ISO particle count. It's operating somewhere in the neighborhood of, say, 20% of its relative component life, where the system on the right was operating somewhere around 171411, which is almost right where we would expect to see about 100% of that component life. Now, these ideas hold true regardless of the type of component. It doesn't matter if it's a rolling element bearing, an engine, a hydraulic system, or a gearbox. The cleaner the system, the more relative component life we can anticipate getting out of it. So when we're talking about particle contamination, we have to really try and figure out, well, what's the best way to address this? Do we address it after it gets into the system? Do we address it before it gets into the system? Do we address it at the point we receive our new lubricants? What are we doing to really address the amount of particle contamination in our lubricant? And there's a couple of things we can do here. When we're talking about contamination control, we're really talking about two types of control. And one would be contaminant exclusion. This is where we want to exclude the contaminants from getting into our system in the first place. Right? We know that there's going to be particle contamination, moisture contamination in the environment around our machine. So we want to exclude it from getting in. We do that with desiccating breathers, particle removing breathers as well. But what about the new oil? What about the new oil that we're putting into our systems? Really, how dirty is the new oil, or how clean is the new oil? Right? We have to really understand what we're talking about here. Now, there's been several studies done over the past 20 years looking at new oil cleanliness. And some of the studies that I've seen include every major lubricant manufacturer around the globe, looking at every type of product, whether it's hydraulic fluid, turbine oil, engine oil, looking at all different types of packaging. So 55-gallon drums, 5-gallon pails, 300-gallon totes, bulk deliveries. And all of the research that I've seen suggests that there really is no consistency from one supplier to the next, from one OEM to the next, or from one package size, or from one product to the next. With very, very few exceptions, the new oil is not clean enough to use immediately in most applications. Now, that's not to say that you can't get new oil that's very, very clean. You certainly can. But unless we're asking for it, unless we're testing for it, unless we're paying for certified clean oil, chances are it's not what we're receiving in our warehouse. So because of this, new oil needs to be filtered before dispensing into our components and into our machines. New oil just has to be considered too dirty. All right? So this is the first step. The new oil comes in the door. Let's pre-filter the new oil. Now, when we're talking about pre-filtering the new lubricant, my rule of thumb is I like to pre-filter the new oil 2 ISO codes cleaner than the target cleanliness of the component it's intended for. Right? So if the component is a hydraulic system, it's got very sensitive servo valves or proportional valves installed on it, we want to make sure that we get that new oil 2 codes cleaner than that target that's intended for. So if it's 16-13-11, we want to make sure it's 14-11-9. And that's really so that during transfer to the piece of equipment, if we do come across some contamination from a top-off container, or because we have to expose the system to the environment, because we have to open up a breather or a fill port, we can absorb some of that contamination without affecting the overall level of contamination in the system. So, some of the other things that we do or perhaps not do is we allow contaminants to enter the system. We use vent caps and breathers that aren't necessarily targeting the clearance size particles that we're most interested in. We've all seen the gooseneck or the open vents. We've all seen the filler breather caps on hydraulic systems. We've all seen the automotive engine oil filter used as an air filter. These typically don't target the 3 or the 2 to 5 micron particles we're most interested in. We have to take it into our own hands to make sure that we're using a filter or a breather that's going to target the clearance size particles, and perhaps also target the moisture depending on the environment in which our components are operating. Right? So we have to take a look at how the components are getting contamination in them. A lot of the times, most of the time, it comes in through the air vents. So let's make sure that we're doing everything we can do to prevent them from getting in. Studies will show that it costs about 10 times to remove particles than it does to exclude them in the first place. So let's make sure that we're doing all we can to address the root causes of the particle contamination. So number 1 and number 2 root causes are particles coming in through the vent and particles coming in through new oil dispensing. And this can be challenging sometimes. When you look at a system like a gearbox, for instance, we typically don't have a lot of options for modifying our equipment because there's a lot of things we want to do with our equipment as far as modifications go, as far as accessorizing goes. So first and foremost, we want to make sure we've got a proper breather on the system. Every system is going to breathe, right? So when the system breathes, we want to make sure we offer a path of least resistance, and that path of least resistance should be able to strip the air, the incoming air, of particles at the clearance size, so 2 to 5 microns, and also strip the air of any kind of moisture, right? Moisture is just as damaging when it gets into the component as solid particles are. We also want to make sure we do a lot of other things. We want to make sure we've got quick couplers on our systems. Quick couplers for filling. We don't want to have to fill our systems or top off our systems or change the oil in our systems while having the system exposed to the environment, especially the operating environment, right? So we want to use quick couplers coupled with filter carts and dispensing pumps with filtration so that we can keep a closed system, right? We also want to make sure we can take an oil sample properly, right? We want to have a sample valve permanently installed somewhere on the machine that gives us a representative indication, representative sample that gives us a snapshot of that system that's truly representative. We also want to do away with things like dipsticks. Dipsticks are a great source of contamination. Think of how we use a dipstick in the first place. We're using it to check the oil level on our systems, but we have to expose the system to the environment. We have to expose the dipstick to, perhaps a dirty rag, we got from our back pocket, just to check the oil level. So when you look at a system like a gearbox that maybe only has one fill port and one drain port, and we want to add a breather, we want to add 2 quick couplers, we want to add an external level gauge, we want to add a sample valve. That's a lot to do in only 1 or 2 ports. So we have to sometimes be creative on how we do this, but certainly we want to make sure all of those things are occurring. We want to make sure that we're maintaining this closed system. All of the regular lubrication tasks that we need to do, like check oil level, add oil, take an oil sample, we want to do them in a means that's as non-intrusive as possible, and that means accessorizing. And when we do have accessories installed, things like quick couplers, it makes it really easy for us to keep that system clean, right? So when we want to dispense oil, we use the filter cart to dispense oil into the system. So we've not opened the system to the environment. We're pushing the oil through a filter before it goes into our reservoir or our sump. If we want to periodically decontaminate, use a filter cart on our system, circulate the oil through a filter cart, well, we can do that with quick couplers without exposing that reservoir, the lubricant in the reservoir, to the outside environment. And also topping up smaller systems, right? We want to make sure that we have a method of certainly topping off our systems that is as non-intrusive as possible. Now, I understand there's going to be some, smaller conveying gearboxes and smaller pumps that we're not going to necessarily outfit like we would a very large gearbox or an agitator. But we still want to make sure that we maintain as closed a loop as possible. So, top-off containers with pumps on them, a hand pump with a quick coupler on the end of it. So we've added new oil to the oil transfer container. It's been pre-filtered 2 ISO codes cleaner than the target cleanliness of the component it's intended for. And we can walk up to the smaller component, the conveying gearbox or the small centrifugal pump. Perhaps that has a quick coupler on it, a very small, 1/2 inch or 3/8 quick coupler. We can couple on and add oil as we need to, keeping and maintaining that closed system. So let's talk a little bit about the value in controlling contamination, what it's really worth to us down the road. We saw those 2 hydraulic systems. We know that simply operating at a very high particle concentration is going to cost us down the road. If we have to change a system every 2 years as opposed to every 14 years, there's a cost associated with that. And that cost is going to be different for every system. It's going to be different for every plant. But there's a whole lot of value in controlling contamination, and it's our job to really uncover that. We know how contamination gets into our systems. We know how we can remove it. So we've kind of tackled contaminant exclusion and contaminant removal. But really, what's the value? because a lot of us, even though now we know perhaps what we didn't know before, we know that maybe new oil is not necessarily clean oil. We know that we should pre-filter our new oil. But today we're not really, we might not have the means to pre-filter our new oil. We don't have a filter card in our plant, so now our job is to convince our management team, convince the people making decisions with our budgets that buying a filter card or accessorizing our equipment has a lot of value downstream, right? So the job for us as maintainers is to speak the language of management, right? And they speak in dollars and cents. Managers are employed to manage risk and to manage budgets, right? So they don't necessarily need to know or want to know about beta ratios and 3-micron particles and additives and all of these things. But they certainly want to know about something that could potentially impact the bottom line and impact their budget. So it's our job to convert what we know about maintenance and reliability into something that they can really understand and get behind. So we want to pull together some sort of financial analysis. Now, we could speak for many, many hours on how to do this properly, so I'm really just going to skim the surface on how to do this and why we do this, and really what the value is downstream. So, our job is to work with a cross-functional group of maintenance management folks, not just the maintenance manager or the plant manager, but we want to talk to the people doing the work. We want to make sure that all of the stakeholders in lubrication are involved in this conversation to really understand what the costs associated with poor lubrication are. And the reason for that is we typically, in plant environments, we typically don't track the type of information that we need to really get a handle on what those downstream costs are. So we'll work with plant maintenance management to estimate the amount lost each year due to imprecise lubrication or poor lubrication. We're going to develop an action plan to help close the gap. This is the most important thing. It's one thing to say, hey, we're doing something wrong here. You should change what you're doing. It's another thing to say, this is what you're doing wrong. This is how you can fix it. This is what you need to close the gap, right? It's also important that we estimate the upfront and the ongoing costs of improving our lubrication program, right? Certainly when we ask our management team for financial support, we want to make sure that, there's no surprises. So estimate, very liberally what the costs are, and let's be a little bit more conservative on what the benefits are. We'll talk about that in a couple slides. So using that information, we're going to pull together a 5-year net present value and an internal rate of return. So in today's dollars, what is this worth to us down the road? What can we expect to achieve down the road as far as a business case analysis goes? So, when I sit down with this cross-functional group of maintenance management, I like to ask several questions, right? So the first question I always ask to get a real understanding of the financial impact is, I ask the team, what's your maintenance budget? In a typical year, what do you spend, on maintenance, right? So, most maintenance managers understand that this is a number that their job is to make sure that they achieve this number. They don't want to go too much over this number, and they typically spend almost right up to this number every year. But in this example, the likely case for this plant was $9 million. This plant had a $9 million maintenance budget. Now, oftentimes I'll ask a follow-up question which involves their production manager, and I'll ask them, in a typical year, how much do you lose due to unscheduled downtime or slowdowns or off-spec production? Now, if there's some subjectivity built into this number, in my opinion, it's best to leave it out. If there is a very black and white number that we can use in this business case analysis, then I add it in. In this example, we elected to leave it out. So the next question then was, of your total annual maintenance cost, so of that $9 million, how much of that is spent on repair work, right? And as maintenance organizations, that's typically what we do, is we repair things, right? So this number is typically very high. So In this example, the maintenance planner is the one that had perhaps the most insight into how much of the work he's planning is actually fixing things. So in this case, 80% of $9 million is being spent on fixing things. As a follow-up question, we ask what percentage of this repair work is being done on rotating or reciprocating equipment, right? So of the repair work, how much is being done on components that have lubricated, that are lubricated, right? It doesn't mean that the repair has been done on the lubricated component, but that machine has lubricated components on it. So in this case, we're talking to the mechanics and the millwrights. They're the ones doing the work. They're the ones that will typically have the greatest insight into how much is being done on lubricated machinery. In this example, it was 50%. Then we ask of the scheduled or the unscheduled repair tasks that we're doing on lubricated equipment. In your estimation, how much of that is due to poor lubrication? Now this is a challenging question because usually when I'm working through this exercise with the maintenance management team, they're just learning themselves that they've got some instances of poor lubrication. Perhaps they're using the wrong lubricant or too much lubricant or lubricant with the wrong additives. So I'm sort of coaching them a little bit on this, saying, you guys have selected the wrong lubricant in these cases. You're not targeting clearance size particles with filtration in these cases, and so on. So as a group, or if the mechanic or the lube tech has some insight, we've ended up at 45% for this number here. Now the last question I usually ask the entire group, I ask them, by implementing a well-defined lubrication program, how much of the problems seen in the previous question could have been avoided, right? So in this case, really what we're saying is, with all the financial support and management support, do you think you could eliminate all or some of the problems associated with poor lubrication? So in this example, it was about 35%. So we put some financial figures against this. We've got $9 million maintenance budget. $7.2 million was due to repair costs. $3.6 million of that was spent on lubricated equipment. $1.6 million was the percentage of lubrication-related problems. So that number there is very important. That is the estimated annual losses due to poor lubrication. That is the total benefit that we can see if we were to eliminate all of the root causes to poor lubrication. But $567,000, or 35% of the estimated annual losses due to poor lubrication, is what the plant feels that they can address. And there's a lot of reasons for that. There's a lot of reasons why that number is not 100% and why it's a third of the total lubrication losses. And a lot of times it has to do with the culture of the plant, the age of the equipment, the age of the plant, the process, the demands on their equipment. And sometimes they just don't want to shoot so high. They want to be a little bit more conservative, when they're talking about what they can actually achieve. So we take these numbers and then we push them into a 5-year macro business case analysis where we're looking at, what the upfront, the ongoing costs are. So when we plug all those numbers in here, we look at the upfront costs being about $345,000. Now this is a very liberal number. In most cases, it wouldn't cost that much money. It wouldn't even cost half that amount of money. But we're looking at, all the costs associated with accessorizing our equipment, perhaps overhauling our lube room, getting an oil analysis program off the ground, installing sample valves, starting really from nothing. And starting from nothing in a very large plant with a $9 million maintenance budget can be very, very costly. So in this case, the example was about $345,000. And then we looked at the ongoing costs. So there's going to be costs for consumables. Perhaps we want to make sure we have a training class, a refresher class for our lube techs or millwrights, mechanics, PM mechanics every year. There's a cost associated with that. So between the consumables, the oil analysis costs, the training costs, and so on, it looks like about $60,000 a year is going to be spent keeping this program floating. So, when we look at that and we discount it, we have to add a discount rate because the discount represents essentially the cost of carrying capital. We're going to invest in a program. There's a cost associated with carrying that capital. So we discount the dollars going forward for the next 5 years by 15%, which is a very aggressive discount rate. But again, like I mentioned, we want to be very liberal with the cost and we want to be very conservative with the benefit. So as we discount that, we add up the net cash flow. We discount it every year by 15%. We add up the discounted net cash flow and the 5-year net present value. So over the course of the next 5 years in today's dollars, this program is worth about $1.35 million to us, giving us an internal rate of return of about 145%. Right? So, what we're looking at here is something that most managers understand. They can really get behind it. They could really support it. They know what it's going to cost them to start it. They know what it's going to cost them to move it forward for the next 5 years. And they also know what kind of benefits they can expect. Right? But where most managers really get hung up and where they really question me is this estimated annual lubrication losses, this $1.6 million in lubrication losses. This is where most managers simply don't believe it. They're saying to me, you're telling me that I'm losing $1.6 million every year due to poor lubrication? The question really then is, show me. Show me where I'm losing this money. So a couple of quick examples here before we wrap up in another 8 or 9 minutes. These examples were taken from a foundry that I visited several years ago, and I was doing an assessment of their lubrication program, and I asked the lube tech, take me to your critical equipment. I want to see what you're doing with your critical equipment, how you're taking care of it. So being a foundry, it's very dusty. There's a lot of abrasive dust floating around. He said, well, we have 26 dust collectors. They're very critical to the plant. If the dust collectors go down, the people working in that area of the plant cannot work there any longer until we get it back up. So we looked at these 26 dust collectors. Each of them had a 250 horsepower motor that was being greased every 90 days and had 2 very large 6-inch shaft fan bearings that was being greased every 2 weeks. So the current practice was 6 2/3 fluid ounces of grease per motor bearing every 90 days, and then 3 1/3 fluid ounces of grease per fan bearing every 14 days. And I asked the gentleman, I said, well, why are you visiting the fan every 14 days? Every 2 weeks you go out there and add grease to it. And his explanation, I think, was pretty good. He said, well, these are my most critical pieces of equipment, and I want to get in front of these pieces of equipment as often as possible. I want to hear them. I want to feel them. I want to make sure that they're running properly. And it's just like every day we get into our car, one morning we turn it on, and it just doesn't sound the way it should sound. So we know something's kind of happening there. And that's kind of the outlook he had on this as well. So I took some data and I took some measurements because I really felt like some of the volumes and frequencies may have been off a little bit. So the calculated practice would have been adding 1.35 fluid ounces of grease per motor bearing every 90 days and 5.5 fluid ounces of grease per fan bearing every 30 days. So he was really close on the fan bearing volume, but he was way, way off on the motor volume. So I made some assumptions to generate some conclusions. The cost of grease being 40 cents an ounce, the cost of labor fully burdened, a full-time employee being $25 an hour, and the time per shot being about 4 seconds. When we add grease, we want to make sure that we're adding grease slow and steady at 3 to 5 seconds per shot. So I took the average being only 4 seconds per shot. So some of the conclusions, using the calculated regrease volumes and frequencies on the 26 dust collectors, we'd save about $1,750 a year, which really only has a 5-year net present value of about $5,800 or $5,900. But what we really found here was he was spending an extra 40 hours per year over lubricating these dust collectors, right? So 40 hours per year in a world-class manufacturing environment. World-class wrench time is about 50%. So if this facility, which I don't believe it was operating at a world-class level, that's 80 hours per year. I would imagine they're somewhere around 30% wrench time, which means that now all of a sudden they've got 120 extra hours or 30 hours, or sorry, 3 weeks every year where this lube tech could be doing something value added, something like taking an oil sample, something like using a filter cart, sitting through a training class or a webinar, right? That's where the real value comes in. We also have to make sure that we understand that in this case, the lube tech was actually using the wrong grease. You know, he was using a grease that he was actually using a 220 EP grease, and these fan bearings required a 100 centistoke base oil grease with anti-wear additives. So it doesn't even account for the loss of production or the loss of usefulness when these things fail. So that was just one example. The other example, I said, well, I knew they were going through a lot of bearings every year and a lot of electric motors. A lot of discussion around the cost of that. So I asked them, well, let me know how much you're spending every year in electric motor rebuilds and purchases and bearing replacements every year. So from 3 different vendors, we came up with the numbers that you see in front of you. Almost $66,000 in electric motor purchases and rebuilds in 2011. And what's really frightening was that they were spending almost $1.5 million between 2 different vendors in 2011 for bearing purchases, not including electric motors. Right? So a lot of money being spent on bearings. So if we apply, you know, industry accepted statistics on electric motor failures being 50% due to bearing failures, and estimated 95% of all bearing failures being premature, and then 58% of bearing failures being due to poor lubrication, you know, we get some really staggering numbers here. So $65,000 or $66,000 of electric motor purchases times the 50% that are due to bearing failures times the 58% of those bearing failures due to poor lubrication, we come up with a number just south of $20,000 a year due to poor lubrication. We use those statistics against the almost $1.5 million in bearing failures, and we multiply that by the 58% of bearing failures that are due to poor lubrication, contamination, over or under lubrication, or wrong lube selection, and we get, you know, almost $870,000 in avoidable lubrication failures, right? So when we start to add these things up, you know, we start to get a really big number here, right? So we know that in this example, the addressable lube losses were $1.6 million. The plant themselves felt they could address about a third of those, so $567,000. Right? So the benefits, you know, the first example, the first case study was the dust collectors. We could save $1,750 per year. The second study was the electric motors. We had about $19,000 in avoidable losses there. And then the third study on the bearing purchases, we had about $870,000 in avoidable losses there. You know, so we add all those up. We take away the $345,000 it takes to get this program off the ground, the initial investment or the upfront cost, if you will, and we take away the benefits, and we're left with about $544,000, which is really close to the addressable lube losses that this plant felt that they could take on in the next year. So you have to remember too, I was walking through this plant for maybe 4 or 5 hours, and I came up with, you know, really only 3 examples. Had I been walking through the plant for a week or 2 weeks, I bet I would have found literally hundreds of examples where they could have done something a little bit differently and yield very, very big results, right? So really, you know, at the end of the day, a lot of the things we do or don't do is causing a huge financial impact on our plant, and there's a lot of money in avoidable losses that we can be taken care of. So I'm just about out of time. I wanted to thank everyone for joining me this morning and this afternoon. That's all for me. If anyone has any questions, feel free to email me or email the folks at Test Oil.
All right. Jason, thank you so much for presenting that. That was great information. Like I had said at the beginning, there's going to be a survey that gets emailed out following in just a few minutes here, and there will also be a link to the presentation on that as well. So again, thank you everyone for joining us, and thank you, Jason, and have a great rest of your day.
Thank you.